So let's get started. Is that okay?
Mm-hmm.
All right. So welcome back to the afternoon session of this Tuesday. And our first speaker is Gautam Iyer from Carnegie Mellon University. And he'll be talking about anomalous dissipation in passive scalar transport.
So thanks a lot. Right? Happy to be here virtually. Right? I'm somewhat sad to not be here in person. Right? So before I get started, let me acknowledge my collaborators. This is some joint work with Theo Drivas, Tarek El Gindi, and Inji Jiong, who I've never met in person. I've only Zoomed with him, right? So, right. Also, just to make things easier, I just put my slides in chat. So if you want to scroll down or back, feel free to do that. Right? The paper is on the archive. It's right, so it should be easy to find. If not, I can put a link. Okay. What's this about? So let's start. So here's the deal, right? So let's start with passive scalar transport. Right? So if I look at, let's say, a dye in fluid, so I have the standard advection diffusion equation, dt theta plus u dot grad theta minus kappa Laplacian theta equals 0. And since I'm going to be taking limits as kappa goes to 0, I indexed everything. Okay, so theta superscript kappa is the diffusion index. Think of theta as temperature in a fluid or concentration of a dye. I always normalize it so that it has mean 0. So integral theta naught equals 0. And this is, of course, preserved by the evolution. Right? And I always have periodic boundary conditions. Okay, so I do this on the torus. And of course, since we're in a fluids conference, I'm also divergence free. Okay. So what's anomalous dissipation? So if I just look at the passive scalar, let's measure the L2 energy loss after time t. Right? So multiply by theta, integrate, it's a standard calculation. Well, half the initial L2 norm square minus half the L2 norm at time capital T square is exactly the integral from 0 to t of norm of gradient theta square times the diffusivity. Right? So kappa times integral 0 to t of gradient theta square in L2 measures my L2 energy loss. Right? If I think physically what happens, right? Well, I have the advection term, and this advection causes filamentation and mixing and high gradients, right? And then I have diffusion, which evens it out. So, I mean, in certain turbulent regimes, this is expected to balance. And what you see as, what you're supposed to see as kappa goes to 0 is that this guy, right, that measures your energy loss. So kappa times integral to 0 to t of gradient theta square is bounded below by something that's independent of kappa. All right. So over here, chi is strictly positive, is independent of kappa, and that's the initial energy norm. Right. So this is known as anomalous dissipation. Right. The main result that we have, right, which I'll show you in a second, is an explicit deterministic example of anomalous dissipation. Right? So if you have any questions at any time, feel free to either put it in chat or unmute. Right? Right. So let me start out by stating what my results are. Right? So what we have are two things. Right? So in the first example, right, I need okay, so let me go through this slowly, right? So I'm defining capital psi to be the set of all pure harmonics, right? Either sin x sin y times a frequency, or cos x cos y, or some mixture. It's just pure harmonics, no sums. Okay, let's throw out the constants and call this set capital psi. Yeah. Now I claim that for any alpha less than 1, right, I can find you a velocity field, u, right, that produces anomalous dissipation for initial data close to this set. right? So let me just go slowly about these conditions, right? So the regularity of my initial of my velocity field is the following, right? So it's smooth before time capital T. Okay, at time capital T, it goes a bit crazy, right? You'll see that, right? It's integrable in time with values in C alpha for any alpha less than 1, right? And it's bounded. Okay. So I can find you a velocity field in this regularity class such that if I start with regular initial data, H2 initial data, and I need my initial data to be close to pure harmonics, right? So if you look at this condition here, it's basically saying I'm in some cone close to the pure harmonics, right? And the width of this cone is dependent on alpha. It degenerates as alpha gets larger, right? So if I have initial data in this cone, I can find your velocity field in this regularity class that explicitly exhibits anomalous dissipation, right? And this constant over here, chi alpha, is independent of kappa and independent of the initial data. So over here, this came with a second condition, right? Which is my initial data has to be close to pure harmonics. If my initial data is anything arbitrary in H2, I can still do it, right? The same velocity field works. It gives you anomalous dissipation, except the rate that you get over here depends on the initial data. Okay. So again, this is all passive scalar transport. U is something that I choose, right? It's much harder to do this if you're solving nonlinear equations, right? So, yeah. So that's our main result. Let me, before I go into what goes into this, right? Here's a cute corollary on non-uniqueness of the transport equation. Okay. So if you remember, I mean, so this transport equation has a nice history, right? So you go, if I just solve dt theta plus u dot grad theta equal to 0, right? If I solve this with the Lipschitz velocity field, then solutions are perfectly unique, right? We learned this in ODE 1, right? The nice results of de Perna-Lyons in 89 said, hey, look, if I want to solve it with rougher velocity fields, right? So here U is L1 in time with values in W11. Right? They have this notion of renormalized solutions and they stay unique in this regularity class, right? And then Ambrosio extended it to, instead of L1 in time with values in W11, he changed it to L1 in time with values in BV, right? Renormalized solutions are still unique, right? And if you go below, there are counterexamples, right? So there was this Zienman counterexample in 78, Colombi, Rowe, and Jeff Rausch in 03. There was an example by DePau also around 03. And then recently, well, okay, so 6 years ago, there's this example by Giovanni Alberti, Gianluca Crippa, and Bianchini, right? That gives you non-uniqueness for a time-independent velocity field U in C alpha, right? But as far as I can tell, this is an abstract existence proof, right? It's right, yeah. So if we have this example of anomalous dissipation, I just wanted to point out that there's a super cute corollary you get about non-uniqueness, right? The example we have tells you that, hey, look, I can find you a velocity field in the same class that I constructed before, right? So it's bounded, it's smooth except at one instant of time. It's integrable in time with values in C alpha. Alpha is less than 1, okay? So for this velocity field, there's non-uniqueness of the transport equation. And the proof is cute. Let me just show you the proof really quick, okay? So here's how I would do the proof. If you grant me the anomalous dissipation theorem, which I'll prove in a second, right? I'm going to pick U to be the velocity field that gives me anomalous dissipation, right? So I know that kappa integral 0 to t norm gradient theta kappa L2 square is bounded below by something. Let's call it chi. Okay, times the initial data, let's ignore it, right? Okay. So now what I'm going to do is let me double time. Instead of going to time big T, let me go up to time 2t. All right. And then between time big T and 2t, let's time reverse it. Yeah. So u of t is just for time between big T and 2t, right? As just 2t minus u of 2 big T minus t. Right. And now I'm just going to write down two solutions of the transport equation, which have to be different. Right. Solution one, time reverse it. Right. Take the old solution you had up to time t, right, and time reverse it between time big T and 2t. Yeah, so that's the formula. Of course, by time reversibility, this solves the transport equation on the entire interval 0 to 2t. Right, of course, there's some checking to make sure that it stays a renormalized solution at this problem point big T, where the velocity field goes crazy, but that's really minor. It just works out quickly. Okay, so that's one solution. All right. So, and let me just point out for this solution, because my velocity field is smooth, except at one time, all right, I know that my L2 norm, right, equals my initial L2 norm, right, so probably it's also true at big T, but I don't care about that for now, right? So here's the second solution. I'm going to take the Inviscid limit of, or the vanishing diffusivity limit of solutions with this same velocity field. Right? So let theta kappa be the solution to the diffusive equations. The standard Aubin-Lyons tells you there's a convergent subsequence as theta as kappa goes to 0. Right? Let's call the limit theta bar. Right? Of course, along the subsequence. Now it's easy to see that theta bar has to satisfy the transport equation, right? With the same initial data, there's no problem with that. Why is theta bar different from my solution theta? Well, I claim theta bar has lost energy. Theta conserves energy, right? So to see that theta bar has lost energy, well, let's look. Let's look at my diffusive guy at some time little t, which is bigger than capital T, right? So fine, so the diffusive guy only loses energy, so the energy has to be less than or equal to whatever energy I had, this is L2, whatever energy I had at time capital T, right? But hey, this is my anomalous dissipation result. At time capital T, I have lost a strictly non-zero fraction of my initial energy. Right? So now I have this diffusive solution such that after time capital T, my diffusive solution has necessarily lost some energy, right? And this, let me just, okay, of course the diffusive solution loses energy, but the point I wanted to make is that I've lost a certain amount of energy that's independent of kappa. Right? So now when I take the limit as kappa goes to 0, right, after time big T, right, the theta bar that I got, right, has to have lost some energy, and hence it has to have less energy than my time reverse solution. So these two solutions have to be different. Right? That's acute application to non-uniqueness of the transport equation. Let me go into the proof of, let me go a little bit into what goes into the proof of the main theorems, right? So what we do is essentially two things, okay? So one, I want to prove some criteria on the Inviscid equation that guarantees anomalous dissipation. I say, okay, if you give me certain bounds on solutions to the Inviscid equation, then I have to have anomalous dissipation. And then step two, we find an example that satisfies these bounds. Okay, I'll be a little bit less detailed about step 2. Right, I'll show you what it looks like. Step 1 is super cute, and I can explain most of it. Okay. All right. So here's the criteria that guarantees. So it's a criteria that's just assumptions on the Inviscid equation, right? And it guarantees that the diffusive guy has to have anomalous dissipation. Yeah. So just to remind you of notation, theta without kappa is transport equation. Theta with kappa is advection diffusion equation. Always same initial data means 0 periodic boundary conditions. Okay. So what are my assumptions? So first, let's take the transport equation. I need to insist that up to time t, right, the H1 norm blows up. Right. So integral 0 to t of gradient theta square in L2 is infinity. Right. Then I need to make one of two assumptions. Right. Either when I look at the norm L2 times the norm H2, it's bounded above by H1 square. Right. I'll say more about this in a second. Right. Or alternately, instead of that, I want to look at norm H minus 1 times norm in H1. This is bounded above by L2 square. I'll say more in 1 second as well. Right. And again, to point out, both these assumptions are for theta, right, which is solution of the Inviscid equation. Nothing about the diffusive equation yet. Right. So under these conditions, I claim that not only do you have anomalous dissipation, I can tell you exactly what the constant is. Right. So I'm missing the initial data here. My apologies. Right. So I claim in this case, anomalous dissipation holds. The constant that comes out, that constant chi, is exactly 1 over 4c to the 4th power, where c is this constant, right? Or that constant. It's the same thing either way. Yeah. So just a quick remark. If I look at the L2 norm of the Inviscid equation, well, this is conserved, right? So norm theta at time t in L2 is the same as norm theta naught in L2, right? By interpolation, right, I suddenly know that if I look at the H1 norm square, I can interpolate that between L2 and H2. My assumption is the opposite. Right? You see, H1 square is less than or equal to L2 times H2. I've assumed the opposite. Right? Right? Same thing for this guy here, right? By interpolation, right, L2 square is bounded above by H minus 1 times H1. I've assumed the opposite. Right? Yeah. So under these assumptions, you have to get anomalous dissipation. Right. So let me show you how this works. There's 2 steps in the proof. Right. Step 1 is a super cute functional analysis observation, which you can put on your homework exercises for your students. Right. Proof is just Cauchy-Schwarz. Once you realize it's true, it's not easy to realize it's true, right? And or realize that this is exactly what you need. But once you do, the proof is really quick, right? So here's the observation. Let me take a sequence of functions in H1. Okay. And okay, I can work with either of these balance assumptions. Let me work with the first one first, right? So suppose that I had norm of Fn H minus 1 times norm of Fn in H plus 1 is bounded above by norm of Fn in L2 square, right? So then I claim if I choose big N to be the ratio, so I forgot the C over here, my apologies, right? So if I choose big N to be this ratio, which is I look at the H1 norm of Fn divided by L2 norm of Fn. Yeah. Find an integer close to that and project onto all Fourier modes after big N. Yeah. The amount of L2 energy you have left in Fourier modes after big N is at least a constant fraction of your initial L2 energy. Right? So it's just an observation that if you have this reverse interpolation inequality, right, then you retain a constant fraction of your energy in the high L2 modes. Right? So again, Pn is just the Fourier projection onto modes larger than N. Right? Of course, if you add to this the fact that if I look at H1 over L2 to diverge, then you can't have strongly convergent subsequences. Right? And exactly the same sort of inequalities are true if you have the H2 and H1 balance. The proof is just simply a Cauchy-Schwarz. Right? So this observation simplifies things a lot, right? In fact, our first iteration of the paper didn't have this observation in it, and the proof was a lot more complicated, right? And then out of the blue, like Tarek emailed us saying, hey, here's a simple observation. You can just simplify everything, right? So yeah. Okay. All right. So lemma 2, right? I claim, so this is a little bit more involved, but okay, let me go through it, right? So I claim that if, suppose for the Inviscid equation, I had integral 0 to t of norm gradient theta L2 squared to be infinite. This is the same assumption I make in the proposition. Yeah, but in the proposition, I have these balance assumptions between product of L2 and H2, right? Or product of H minus 1 and H1. Let me replace that with what I've learned from the lemma, right? If I had those balance assumptions, then I know that I retain some energy in the high Fourier modes. Right? Let me just make that as an assumption. Okay, so I assume that the H1 norm blows up when I integrate in time. Right? Sorry, H1 square blows up when I integrate in time. And I assume that I keep L2 energy, right? I keep some constant fraction of L2 energy in high modes, right? How high? The big N, the frequency I project on, should be comparable to the H1 norm. Right? So if I make this assumption, then I claim you have anomalous dissipation, right? And you have an explicit constant. So whatever this constant C was is exactly what comes here. Yeah. So just a quick observation, which I just said, if I just looked at that lemma 1 I had above, plus the balance assumptions in the proposition, right? I immediately get this thing over here. Right. Sorry, my bad. I immediately get that I have energy in the high Fourier modes, right? Which is, right. So in this sense, I mean, the lemma that we have here is stronger than the proposition I stated initially. So let me show you quickly how this proof works, right? So how do you get anomalous dissipation based on these assumptions, right? So the first thing is to note, okay, so theta satisfies transport equation, theta kappa satisfies advection diffusion equation. I can subtract the two equations, multiply by theta, Cauchy-Schwarz, do the standard thing, right? And then if you do that and write it out, here's what you get. So the difference between these two in L2 is bounded above. I want to split it like this, okay? So there should be a kappa on the right. I'm going to split kappa as square root kappa in each term, right? One of the terms is integral in time of the H1 norm square, right, of the diffusive scalar. The second one is the integral in time of the L2 norm square of the transport equation, right, the Inviscid scalar. Yeah. So I'm trying to convince you there's anomalous dissipation, which is I'm trying to show you that the red term is big. Let's suppose for a second that the red term is small. Right, I think I'm missing a gradient here. There's a few typos, apologies, right? Okay, so if the red term is big, there's nothing to do, right? I've got what I wanted. So let's suppose that the red term is small, right? So how small? Let's put it some constant times the norm of the initial data and pick this constant to be smaller than the chi, right? Which I stated in the theorem, right? So I'm looking for a contradiction, right? So if, right? All right. So, right. Just for simplicity, let me pretend this constant big C is half, and the initial data has norm 1, right? Of course, pretending that big C is half, right, is not entirely fair, right? If I look over here, you're telling me that I retain all my energy in the high Fourier modes, right? Okay, but it just simplifies what I'm saying below, right? It's not a serious assumption. You just put C and trace through the constant, and it works out, right? Okay. All right. So I assumed that the Inviscid scalar, when I looked at the integral of the H1 norm square, I assumed that diverged, right? Okay. So no matter how small you make kappa, I can always find an epsilon small, so that when I integrate up to time t minus epsilon, the second factor is 1, right? So now what do I have, right? So if I look, okay, I called the red factor, right? So which is the integral in time of the H1 norm of the diffusive scalar square. I call that delta, right? So now there's this extra square root here. So I say, okay, if I can make the second factor roughly 1, difference in L2 norm between theta and theta kappa is roughly square root delta, right? All right. So by my assumptions and normalizations, right, the amount of energy I have in L2 in the high Fourier modes is order 1, right? Yeah. So now, since theta and theta kappa are close in L2, right, I can do a triangle inequality and say, hey, the amount of energy I have in the high Fourier modes of the diffusive scalar is still non-trivial. It's of order half at least, right? Just because the projection is uniformly bounded in L2, right? So now we're in business, right? I'm telling you that the diffusive guy retains a significant fraction of its energy in high Fourier modes, right? So what does that mean? If I look at kappa times the integral in time of norm of gradient theta kappa L2 square, right? That's my anomalous dissipation thing, right? This is bounded below. Well, I can take the H1 and replace it by big N times the L2 norm of this, right? So I'm just doing that over here, right? What is big N? Let me remind myself. Hey, look, big N was the H1 norm of the inviscid scalar, right? So plug that in over here. Instead of big N, I get the H1 norm, right? By choice of time, right, the H1 norm of the inviscid scalar was roughly order 1, right? Sorry, kappa times the H1 norm of the inviscid scalar was roughly order 1. So if we keep track of all constants, you get a lower bound on the energy dissipation, right, or the entropy, right? So that's basically how the proof goes. Yeah. So before I go further, let me spend a couple of minutes talking about connections to mixing, right? So if you look, right, our criteria that guarantee anomalous dissipation are the following, right? So I just rewrote it over here. Assume integral in time of the inviscid guy in H1 square, it blows up. And I assume my reverse interpolation. So H minus 1 times H1 is bounded above by L2 square, right? That guaranteed me anomalous dissipation. Sorry about this. I keep losing the initial data because of cut and paste, right? Right. Okay. Well, I know something. Well, H minus 1 decaying, right? So these are these standard things about mixing. Let me go that direction for a minute, right? Suppose my velocity field U was exponentially mixing. So what does this mean, right? Exponentially mixing tells me that my some measure of the mix scale, in this case, let's just choose the H minus 1 norm. This thing should decrease exponentially. right? So let's put constant and say, hey, this is bounded above by e to the minus some constant t times the initial H1 norm, right? Because just remember, right? So the transport equation is time reversible. If I want to look for mixing, right? I got to take a weak norm on the left and a strong norm on the right, right? Otherwise, I can destroy this inequality by just reversing time. Right? So that's the definition of exponential mixing, right? So that would take care of the first term over here. That decreases exponentially. How about the second term? Well, the H1 norm, I know this, right? H1 norm of solutions to the transport equation, this grows, right? So certainly I know that the H1 norm is bounded by some exponential times the initial H1 norm, right? So, I mean, the crudest bound would be, I could just choose the prefactor to be 1, right? And the exponent, the exponential decay, exponential growth rate to be the Lipschitz norm of the velocity field, right? Just Gronwall out and you get this exponential growth, right? Of course, you can do better bounds, right? There's this Kripper-Delelis paper, right, that says I could put, instead of L infinity, I could try doing an LP bound, and that still works out, right? You get some growth, but okay, maybe there's a prefactor that depends on theta, right? Fine, right? Okay, so the H1 grows exponentially. If U is mixing, the H minus 1 decays exponentially, right? The L2 stays constant. Yeah, I want the product to be bounded above by the L2, right? So I want the product to stay bounded. This is only going to work if the constants match, right? So the exponential decay rate of the H minus 1 norm has to match the exponential growth rate of the H plus 1 norm. Yeah. So I need exactly the same constants in both these estimates. And we call this optimally mixed. I have no examples, right? I don't have a single example of a flow and even one initial data that gets mixed optimally, right? In fact, if it does, it would address a few things I spent some time thinking about, right? If you look in the sense of enhanced dissipation, right? How fast do solutions to the advection diffusion equation lose energy? Normally, it's e to the minus kappa t, right? But if you have this fantastic assumption here, you actually get e to the minus t divided by log kappa, right? It's better than you can just get in terms of mixing assumptions, right? Which is, I spent some time thinking about it and I couldn't do it. Right? But regardless, even though we don't know an example that gets us this optimally mixed initial data, for the H1, H2 balance, we have an example. That's what we do to prove the theorem, right? So let me just show you what the example looks like, right? What time am I supposed to end? How much time do I have left, Milton? Right. About 10 minutes, I hope. Right. So
yes, you have 10 minutes.
10 minutes. Okay, thank you. Right. So
15 minutes.
15 minutes. Thank you. Right. I should finish in that time. So here's a sketch of our example. Right. So this is inspired by these velocity fields that Pierre Humbert had in the 90s. Right. So what he did was he took a vertical sine shear and a horizontal sine shear and just alternated them. Right. Of course, this doesn't get you anything. So instead, what he did was he randomized phases. So I take a vertical sine shear and I shifted up or down randomly. Then I alternated with a horizontal sine shear and I shifted left or right randomly. And this gets you like beautiful mixing, right? So he had this in the 90s. So we wanted to do something. We thought something similar would work out over here, right? It didn't quite. We needed some changes, right? So first, instead of taking sine shears, we take sawtooth shears. Right, so let me draw that. So here's a picture of my sawtooth function. Right, so I have a little smoothing. So this distance here is epsilon. Right. So instead of a corner, I smooth it out in some small epsilon neighborhood. just to make the flow smooth. Right? If not, it's perfectly Lipschitz, and that's good enough for me. Right? All right. Then, so I call this S epsilon. So let me draw that over here. Okay. Then I'm going to divide time into a whole bunch of intervals. So here's 0, here's capital T, and let's split it up. Let's go for time half, and then for time 3/4, right? And then for time 7/8, etc. And so these are your TJs, right? And what I do is the following, right? So in the first interval, let's look at a horizontal shear flow, right? With the shear profile being S epsilon. Okay. So for the first time interval over here, I look at a flow like this, right? So that's a vertical shear. And then for the next interval, what I'm going to start to do is increase the frequency, right? And reduce the time. So now I'm going to switch from a vertical shear flow to a horizontal shear flow, right? And I'm going to increase the frequency. So over here, something like that. Right. And then, okay, at this point, I can't draw it anymore. Now I do vertical again, right? And then I flip, right? So every time I increase the frequency and I flip directions, right? And then we show, I mean, somewhat explicitly that you have the reverse interpolation balance that we required in the proposition, right? Which is the H2 norm is bounded above by the H1 norm square if you do this, right? And if you see the way that we choose the frequencies, in this case, Nj is 2 to the alpha j, right? And if you look at, so my smoothing parameter just decreases. I can just ignore that, right? So ignore the smoothing parameter. And J's are the frequencies. This alpha is the Holder regularity you want to keep, right? Strictly less than 1. Okay, so that's where that goes. And let me maybe end with the question about, or a question that we don't know how to do, this dissipative mixing conjecture. It dates back to this nice old conjecture by Bressan, which I thought about a long time ago and didn't get anything, but okay, right? So as before, so theta is inviscid, theta kappa is diffusive, right? And now let's just think, okay? If I look at the inviscid guy, how fast does he mix? Right? So norm theta mix on the left-hand side is just some quantification of the mixing scale. For instance, if I subtract off the mean and I look at the H-1 norm, right? That's all the left-hand side is. Right? You can't mix faster than exponentially. Right? This is a quick calculation you can do by Gronwall and check, hey, look, the mixing scale cannot decrease faster than e to the minus integral in time of norm of gradient u in L infinity. So norm u in W1 infinity, Lipschitz norm of u. Right? That's my lower bound of how fast I can mix. Well, so Bressan in 2003 said, actually, I think the same bound is true, right? But instead of putting norm u in Lipschitz, you put norm u in W11, right? Much weaker, and you get the same bound. Of course, in this case, you have maybe a prefactor that could depend on the initial data. Also, a decay rate over here that could depend on the initial data. He offered a $500 prize, which, as far as I know, hasn't yet been collected. Right? Gianluca Crippa and Camilo Delalis came close. They said, hey, look, instead of W11, if you give me W1P, they proved it. I don't know if Bressan paid them or not, right? But right, it's good enough for me, but okay, right? So what happens in the context of diffusion, right? Well, with diffusion, I don't need to look at the mix norm to see how fast things decay. The energy already for the diffusive equation decays. So let me just stay at the L2 level and see what I can say, right? So the better I mix, the more efficient diffusion is going to be, and the faster my L2 norm is going to decay. So let me look for lower bounds of the L2 bound norm. Right? So there's a result by Poon, which is also in this nice paper by Charlie Doring and Miles in 2018. Right? Again, every time I say this, it's like rest in peace, Charlie. Right? It's a big blow to the community. Right? So the lower bound you have is, well, the L2 decreases, is bounded below by something which is double exponential in time. Right? So e to the minus kappa, right? Certainly I expect that. But you see what comes after the kappa, right? It's again e to the integral of u. So integral of u in time. So this is, right, e to the t inside the exponent. So that's a double exponential lower bound. The optimality of this is open. I don't know, right? In discrete time, I have an example. I can show that this is true. In continuous time is open, right? There's actually a nice discussion in this paper of Charlie Doring and Christoph Miles, which I recommend looking at, right? So question is, can I do the same thing? I ask similar questions as Bressan, right? I say, hey, look, instead of putting a strong norm of u over here, let's put a weak norm. What do I get? Right? So this is the lower bound I have for free, which is double exponential, right? Now, instead of putting Lipschitz norm of u over there, let me change it to the L1 norm, right? So it turns out in that case, I can't hope for the same sort of bound with just kappa. I need to replace it with some function r of kappa where r vanishes. Here's the question, is this bound still true, right? Well, I mean, why is it related? Why are we thinking about this, right? If you look at, suppose this bound is true for a second, right? You add to this the energy inequality, right? Just for the advection diffusion equation. So what does it get you? If I look, it gets you an upper bound on kappa times integral in time of norm gradient theta kappa square, right? What's the upper bound? Well, initial norm, right, times 1 minus whatever this exponential was, right? Let's digest this for a second, okay? So let me not worry about time going to infinity. Let me fix time. Let's fix time to be order 1. And let's fix kappa to be really, really small, okay? So then I can just unravel whatever I have in this exponential and say, okay, so in that case, it should be kappa times integral in time of norm gradient theta L2 square is bounded about by this exponential for small kappa just becomes r of kappa. Yeah. So, hey, look, right? If instead of looking of norm u in W11, I looked for norm u in C alpha, alpha less than 1. I looked at less than 1 derivative. This conjecture has to be false, right? We're at the borderline. We have this anomalous dissipation example. If u is in just C alpha, alpha less than 1, I know this left-hand side is order 1, right? The right-hand side vanishes, right? So there's a nice paper by Brew and Nguyen that suggests that R of kappa should be of order 1 over log kappa. There's also an improvement by Christian Seiss, right? Also, for if I put norm gradient u in LP, for any p between 1 and infinity is still open. I have no idea what happens, right? Loss of regularity for the transport equation makes things hard. I don't know what to do. So I think I'm out of time. Let me stop here. Thank you. Right. Here are the references. Right.
All right. Thank you for your talk. And I mean,
Gautam is talking.
No, Gautam just in. So we thank the speaker, then whichever way we want, we can. And I open for questions now. If anyone has any questions, now it's time to ask them. We have
There's a request to ask a question in chat.
time for some.
Oh, hi, Gautam. Very interesting talk. I have a question. I suppose it's somehow outside of everything you have proved, but I'm still wondering if the blow-up condition you assume on the Inviscid flow, is this strictly necessary for for anomalous dissipation in this model, or
the blow up? Yeah. I think so. I don't think you can get anything without that, right?
yeah, exactly this condition. Yes.
Yeah.
I'm just wondering, motivated by other fluid dynamics equations, like especially the.
Yeah, I don't think I don't have a theorem I can tell you now, but I don't think you can get it without that.
Okay, thank you very much.
Right.
Any more questions?
About these assumptions too, if I can ask. The second one, that constant, no, right on that slide, the same slide. Yeah, this constant on the assumption, actually maybe the one of H minus 1 and H1, that's allowed to depend on the initial condition, right?
Right. So this is, you fix an initial condition. If you give me, I mean, this, as long as this constant doesn't depend on time, right? Whatever that constant is, right, I get you anomalous dissipation with that same constant. So if you can only arrange me this assumption with the constant depending on initial data, then that shows up again over here, unfortunately. Right? And if you're not a pure harmonic, that's all we can do. Right? If you're a pure harmonic, if you're close to a pure harmonic, we can get constants here which are independent of the size.
And you need that condition for every t before the blow up time.
Absolutely. Right.
Thank you.
Any more questions?
Hi, Gautam. I have more of a comment than a question. I just wanted to point out that some recent work of Camilla Nobili and Stefan Pottel, in which they do get some bounds using Fourier splitting methods, but because they use Fourier splitting methods, they can do it only in the whole space, not on the
Camilla
floor.
and who?
Stefan Pottel.
Potter?
Yeah, Pottel.
EL. Thank you. I
Yeah.
didn't know. I'll take a
But
look.
it's on, I think it's on the archive. But it's on the whole space. It's not because they're using this Fourier splitting method.
Yeah, that's a different game.
Yeah, they
altogether.
can't adapt it to the tours. And I also want to mention that one could try to use some, estimates on the Green's function for this equation, for the advection diffusion equation. But I thought about that, but the problem is that you typically need U to be very regular to do that, and then all of these estimates breaks down.
Right.
But it's something maybe to think about longer.
No, absolutely.
Great talk, Gautam.
Thank you.
All right. So I guess we'll stop here. Then there's the poster section, and we reconvene